Over here is not working. Good morning. We haven't seen each other the past 2 weeks, but next week I'm giving 3 lectures, so we'll be able to wrap up. If you remember from the beginning, I'm doing a little bit of a compressed module, and then there are 3 options for you to follow up for the last 4 lectures. So today is the 5th lecture on the structural materials and service. There's an issue. It happens to 1 lecture every semester. So my 3rd lecture, the Friday, February 4th, is not going to be available. So those that were in class, great. Otherwise, it was a summary, a 1-hour summary, more or less, of materials processing. So it was more or less of a summary of what I teach in the fall. So it doesn't change the flow of things with respect to this module. So if you remember, after that, we've been talking a little bit about materials for aerospace, where the weight is very important. So that got us to talk about performance factors for material selection. So we had the material indexes. And then in the flow of things, what we did last week was to go over plastics, because they're very lightweight and they have a lot of advantages. And we'll go back a little bit to that, because it was a very interactive lecture. You guys had a lot of questions on plastics. So we'll do that first today, and then go into more specifically material specifications. And the good thing with material specification is mostly to create your awareness. We don't have to go over all the different ways you can specify material, but at least I'm going to give you a few examples, both for material and also for actual full products. So again, with respect to the polymers, some of the things we discussed last week was most of them are semi-crystalline. So we think of polymers as these macromolecules, except that for most of them, except polycarbonate, for example, and the transparent ones, they have very small crystal lamella in them, and it's organized a little bit like an ice formation, where the crystal portions form a nucleus, and they emerge in all directions. And then you have the crystals and the polymer stacked together. So essentially, it's very hard to take these big chains and organize them in a perfect way by folding them. So whatever leftovers end up between the crystals. It does affect a lot the mechanical behavior, and that's why when we take a nylon cord, it's a lot stronger, because you've broken down by deformation, you've broken down that cast structure, and everything now is a lot more organized. If you have an injection molded part, then it is a lot softer. So your strength can be just of the order of 1/3 the strength that you'll have from the cord. We talked about viscoelasticity a lot. It was essentially discussing that when you wait longer, you can have these macromolecules move more with respect to each other, and that's what transitions you from between an elastic behavior, a viscoelastic behavior, and then what we call a viscoplastic behavior, where you have actual flow of chains with respect to each other over a significant length. There are a lot of applications for plastic, even if we're thinking very demanding application. One thing we discussed last week is the creep limitations, but despite having to deal with creep, you have a lot of unreinforced plastics used for very demanding application, including natural gas distribution, especially in the Boston area. You probably hear or smell natural gas every once in a while. So a lot of the old pipes are leaking. And for distribution, it's since the 1980s, approximately, that people have more or less stopped using metal pipes, mostly for the issues with protecting against corrosion. But essentially, at this point, there are hundred thousands of miles of plastic pipes in the ground, all the way from relatively small, maybe even smaller, to 8, 10 inches that are just polyethylene, which is one of the softest and of the polymers out there. Now, it doesn't come without some risk. So one thing we discussed again was that you can have local deformation. So instead of a crack here, you have a crack, but you still have ligaments. You have fibril in them, and the stability of those trays varies a lot with the molecular weight. So that was a topic we discussed a lot. It's not to say that when you have an amorphous polymer, you can't have some special deformation that either facilitate or stop the crack. So the reason for that image, if you remember from last week, is I was mentioning why polycarbonate is very tough, because by having the crack is going this way, and because you have these shear band forming on each side of the crack, you really are blunting it more, and therefore you increase your toughness, your resistance to cracking by that ability of polycarbonate to deform. So some of the things I wanted you to remember was the effect of molecular weight on the long-term properties. And if you remember, there was a kind of a counteracting effect where if you have high molecular weight, sometimes it's harder to crystallize. So with less crystal in the polymer, you're softer when you do a tensile test, a short-term test, but you're just much stronger against the cracking resistance, was one of the takeaway. Another takeaway was you can save money with plastics, especially if you're thinking that you don't have to provide coatings for environmental protection. But there are some limitations. So I do have a pipe sample here that I want to circulate around. It's cut in half, and you'll see one side is a clean cut that we did with a blade. The other side are a bunch of very slow cracks that started in service and grew all the way through the wall thickness before it failed. So I'll circulate it, and I'll sketch it out a little bit what it says on the fracture surface. And you can look at those, of course, with a microscope, but just with the naked eye, on the side, the side wall that has the pre-crack, you see a lot of little shape like this, kind of half circles. So these are indicating a point in time where the crack was, almost through the thickness, so almost leaking. And it's also what we call a crack arrest line. It means that if at some point I was here and I was there, it means that I started a crack somewhere here in the middle. So the X are locations of crack initiation. So what we learned from that is a lot of initiation site. There wasn't just one big particle that was causing the problem here. There's essentially a lot of location where the crack started. And a good time was spent in growing that crack slowly. Now, this is a fire sprinkler pipe. So it's used mostly light commercial, like MIT. Well, I don't know what they're going to do with the new building, but not a very large institution still use steel for the sprinkler system. But when you're looking into new condominiums or slightly smaller buildings, a lot of plastic is used because it's faster to put together and it's less expensive. You don't have to worry really about corrosion, but one of the issues in this case is contamination. So if there is a little bit of oil from the boiler or any other part of the system that gets into this section of plastic, the oil acts a little bit like a lubricant, so it will facilitate the formation of those cracks here and their growth over time. So it's a very well-known issue. I'd say it wasn't known as much when they started authorizing the use of plastics for fire sprinkler. So there's been a number of issues and a number of improvements to the resin and to the practice of, of installing these systems to avoid having this type of issue. But perhaps, and that's something, unfortunately, we don't have a huge amount of time to talk about, but it's not because you have plastic that you can rule out potential problems with the environment. A lot of plastics will degrade from UV light, and I think from common use, you probably are familiar with that. Just time itself and the water. So if you have plastic pipes that carry potable water, there's a lot of oxygen in that water that will over time degrade the resin, especially polyethylene. So it's a little bit counterintuitive, but some of the very long-term effects are very within the structure. So you can start breaking chains. There's a lot of things that can start going wrong within the polymer. It's not that you're losing section, but you definitely are losing capacity over time. So now, having said that, in terms of the advantages, it's very easy to make a plastic that will have some special shapes. Yes?
Are there any just an acoustic property between these materials? Sometimes in homes you get a lot of noise from the piping system.
That's a very good question. Yep. So the question was about the difference for, house plumbing, more or less, in terms of noise. It's two-folded. So a lot of the noise in a home is going to be because people didn't put all the hangers on. So if you have a copper plumbing system that has the hangers just by the code every so often, there won't be noise, really. If we're thinking as far as the pipe moving, for example, if we're thinking about the flow itself, yes, a plastic will damp a little bit more the flow of the liquid through the line. But this is a topic that I think is very interesting in a sense. When you start using plastics, they expand and contract more with temperature variations. So a lot of the issues that or the rigid plastic, like those fire sprinkler lines, a lot of the issues that you don't worry too much with metal, let's say the metal is going to stretch 3 millimeters over 12 feet. That's not a problem. But if now you have 3 times that amount, maybe it won't go too well. It will actually create a lot of bending if you have too much restraint on your system. And that's something we've seen a few times. Let's say you have a large drain system that's 100 feet and you try to make it straight. They will do that out of stainless steel, for example, because first of all, if there's a problem, the stainless is just going to deform a little bit. It won't crack. It's very, very tough, just like structural steel. But with plastic, you can start having some cracks, just even if it's a one-time movement because of the way the joints are made, if you have solvent cement. And mostly also because now you're talking about inches of movement over that 100 feet of length. So instead of being 3/4 inch, it could be as much as 3 inches. And 3 inches, if you have a lateral, it means a lot of movement. So if you're going this way and then the end has to contract 1.5 inches, well, it's making a lot of bending moment on that connection. So there's plus and minuses with respect to just general use. One of the advantages, and that's what I'm showing here, is there's a lot more easy way to make these products without having to put threads that are long to do. When you try to put a steel plumbing system together for fire sprinkler, you have to thread each connection, and you have to do it in a special sequence to be able to build your system. Whereas here, if you're just trying to insert things together, they can rotate after, and you're still holding the pressure. It's not a problem. So like a seal system like this one is just a lot more flexible for use. And it's a way, one of the reasons they came up with this too is this increased expansion, thermal expansion of the plastic. So if we used to have rigid lines, with steel or cast iron, and it didn't really work well with the plastic. So there was another reason to come up with these joints. Yes?
So can you explain what's going on there?
Okay, we have a bell and spigot system. So this end of the pipe grows bigger, and the spigot comes in, and you have O-rings. So the way you put these large systems together, let's say each is 40 feet, you literally slide one into the other, and there you go. You have a system for drainage. No real joining, and in service, you can have this piece move relative to this one as long as you don't get within that shoulder. Because then you start prying the system. So you're supposed not to fully insert these in the ditch to be able to work. Yes?
What are the two pieces sticking out without the...
Yeah, that's a good question. I say just ignore it because this is just really an O-ring going all around. I don't know why. They've sure, I haven't come with the image. They probably have always been there. Good question. But so this goes to the outside, and it's a bigger diameter, and then you insert the other piece in it. And the only reason for three O-rings is redundancy. You know, in principle, you could have just one. Yes?
Is there ever a lot of axial loading that could potentially cause those two pieces to separate?
Very good question. So you can't, about disconnecting this assembly. This is for buried conditions. And the way it typically works is you'll hold a few of those at certain distances, especially if you have to turn, if you have to put a elbow, you have a support there that stays fixed. And between the supports is where you want a certain amount of expansion. But yes, you don't want this to be completely free-floating everywhere. You don't want to put that specific joint into a building, for example. So just the ground itself is holding it in place. And you try to have about, depending on diameter, maybe 1 inch here of extra space to continue to insert. Very good question. Practical engineering. Okay, composite pipes. And this is going to really help us tie into this whole material selection module. I brought one cross section of it. It's not all that clear, but on the upper side, so the side towards the center, you'll see that there's a clear layer. And there's one issue with composites, even though the polymer, is moisture penetration. When you get that polyester resin or whatever resin you're using to be fully absorbed with moisture, you're losing the good bond between the composite and the resin. So to try to avoid that is where you put a coat on it, essentially. So it's not painted, but as part of the design, you have this external layer that protects it, that protects the structural wall. So you have a structural wall, and then you have an isolation layer. The most common way to make composite pipes, if you look at this one, for example, is to have a core and then you wind the reinforcement around it. And the reason we do that, so you'll see there's a little bit at this angle, there's a little bit at this angle, is to increase your pressure capacity. The pressure stress in the circumferential direction is twice as much as longitudinal if it's just a closed cylinder. So you want to reinforce it that way. That's not something that you can do by extrusion. So when we do the extrusion of the sprinkler pipe I showed, you actually get straightening mostly in the direction of the pipe, in the axial direction, and where you want it the most is around the circumference. It's just the way it is. So reinforcing makes sense, and you can make it out on very complex structures. One of the main issues here is joining again. Because if you have your reinforcement, that happens with bicycles and any kind of composites. It's very strong, but then how do you take multiple pieces together becomes an issue. So this solution we just went through together with the O-ring is one that's used also for these composites pipes. You can have some special clamps. You see them here. So hardness clamp that just take two sections and put it together, and a lot of O-rings. But you can see that it's a lot more involved than if I have two pieces of plastic that I essentially glue together, is the way we do the sprinkler pipes. So these are relatively advanced use. So in terms of volume, it's not super significant. But to relate a little bit with our steel versus plastic discussion, this is a large volume application. So storage tanks for gasoline at gas stations these days are mostly composites. You still have, however, people that will buy the steel tanks. Just a little bit on how it works with the composite is you can make use, you see these ribs around the circumference, and one of the issues with an underground storage tank is the weight of the dirt and cars and trucks that are going to be right over it at any point in time. So you need to have this crushing resistance, and we've seen that on some of the previous image. So the failure mode for a tank or a drainage pipe is it starts round, and then it turns into an ellipse over time. And by doing that, you get a lot of stresses here, 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 and here. One of the more important one here is you get tension on the inside at the bottom. That's not really cool. So when you have to put these tanks into the ground to make sure that they have their useful life, you have to support it with good aggregate here to minimize. I mean, you could potentially make a tank that will resist any environment, but that would be too expensive. So in the actual application, the way it's tested for its useful life, the 25 or 50 years life that you want, is you put an aggregate to support the bottom so it doesn't turn into an ellipse. You also, in the design, includes these ribs. So you see they're not solid, they're empty. And so the way this works, just in terms of the manufacturing, is you have your form. So you have two halves of a mold that essentially is the outside profile of the tank. So this one. And then you come from the inside and you start spraying the composite. In this case, it's a resin with some small chop fibers. It's not super expensive. After you've done it for a while and you build up that wall thickness, you start putting a mat across to fill that gap and make a cavity out of it. So from there, you start building up a little bit more. You want a double wall. So what you see here is essentially an air gap, and there are sensors at the bottom of the tank that will tell you if you had fluid penetration through your first wall. So it used not to be this way 30, 40 years ago, but the new tanks essentially have a doubler. If you're leaking through your primary containment, you'll get a signal and you know you have to go and do something. So it's much safer from that standpoint. Yes?
So where is this located on this?
Yeah, good question. The rib goes all around here. So this is the cylinder wall that's straight. And if we go back to the previous image, we're looking at these raised rib here that go around. I can tell you one issue with turning into an ellipse is the compatibility with the end circle. You know, you can squeeze a cylinder and that's okay, but the cap that goes with it, when you start squeezing it, you're getting tension. You don't have a compatibility of your deformation, and that tends to be a failure location. So one reason for wanting to stay round is to not have breaks between the cylindrical portion and the half sphere at the end. It's not easy. But anyway, and some of the issues that happen there with the composite is, again, it won't corrode. This is perfect with respect to the interaction with the soil. But the liquid, when people move from using gasoline to gasoline with ethanol in it, well, ethanol is a different solvent. So they did have issue with some of the polyester resin to build up that wall, and they had more degradation, more rapid degradation, depending on the conditions. So going to the plastic doesn't solve everyone's problem. I guess this is the bottom line. I took this from the 2013 module on material selection I did. It was a full 12 hours there going over these different categories of material. And this is qualitative. I was developing it as we were going through that module, but some of the ideas that I'm trying to put together here is advantages, disadvantages of some of the material. And really, this term, we talked a lot about steel, aluminum, and I've talked to you about plastic composite. I have a super alloy here, and I mentioned about creep. So when you have a turbine, or not just for aircrafts, but also for power generation, it can get pretty hot. So you need materials that are resistant to heat, that won't start to deform at high temperature. And we reach limits so easily. So this one is empty on the inside, not for weight reason, but also for circulating coolant during service. So you circulate air through this, and this one doesn't have it, but a lot of these blades will have small holes where you get the air to flow through the wall and protect the outside surface against the combustion gases. So you're creating a boundary film on the inside of the part as an extra insulation for your resistance. So I'll circulate that one around as well. So, I mean, there's a reason why we use these different categories of material. A lot of time, history helps you make decisions. You know, if a lot of people have tried composites for an application, and these are the three issues, can't really resolve them, then, you know, people move on to do other things. There will be applications just like those underground storage tank from an overall performance, so overall cost. It's hard to tell which one is better. You can buy the tank, you can buy the composite tank for, I think it's trying to remember. I think it's very comparable, and that's why it's very competitive, between buying the plastic tank and putting this aggregate and getting the steel tank and putting cathodic protection. It's very similar, and that's why it becomes a little bit of a preference, which is interesting for a system like this, as to which one you're going to use. So there won't be one material that's going to ever do everything we want. One thing with steel is this brittleness at low temperature, and I decided to bring some samples of that. I'll just circulate 3 of them. This is Sharpie V-notch test. Anybody knows about that? You take essentially a rectangular bar. It's a very standard test, and it's used a lot these days just for, I say, qualitative analysis. And you just machine a notch in it. So let's say we do a V notch. That's what is more common. So you take that off here. And then you're going to hit it with a pendulum with a lot of energy this way, trying to open it up. And the 3 samples I circulate is there's one case, it's almost like a saw cut. There is no real deformation of the metal around here before the crack started and propagated across. So that's what we call a brittle behavior. So it happens when you take your sample and you cool it off just before the test to determine at which temperature upon impact you're going to have a brittle behavior. There are a lot of reasons why it's specific to steel. Maybe the only one that you'll remember is steel, despite all its advantages, is a body-centered cubic. So when we look at it at the atomic scale, we have the cube and we have one atom in the middle of it. And that leaves us with much less slip system for deformation of that structure than if we have an FCC system, so a face-centered cubic like copper, aluminum. Those two, aluminum you can use at very low temperature. If you have a stainless steel that is the type of structure same as aluminum, so a face-centered cubic, what we call austenitic stainless steel, that's what you need to use for cryogenic application. You can't just use steel at these low of a structural steel at these low of a temperature. So there's always a limit, and the reason to do these tests is the limit depends a lot on very small impurities, on grain size, and if you're trying to build a bridge or a ship that's going to be going to the Arctic, then you do need that low temperature toughness. Even pipelines, which is something that I want to discuss with you in details, you have to worry about that. So in terms of the plus and advantages, that's really a disadvantage of steel that and aluminum is the opposite. So aluminum, when we were talking about the aircraft wings, was the opposite. If you heat it up, it softens very easily. So even a structural fire, if you were to make a building out of aluminum, would really be a problem. You can literally cook a small fire and everything becomes soft and melts, while a structural steel side, you would not have a problem. So the day you want to make a building out of aluminum, let's talk about that first. The other elements, when talking about maybe corrosion here for plastics, I put a plus or minus because there are so many things that can go wrong with your plastic that are not, section loss or thickness loss, that I don't want you to come out of the class thinking, if this is going to be used, especially acids, don't do very well with the plastic. You have the UV light. There's just a lot of limitations, not just mechanical, but in terms of the environmental resistance to really think about. Yes?
Is there anything that can be done to coat plastics to prevent UV degradation?
Yes, very good question. So it was about protecting against UV degradation. One of the common ways you put carbon black into your resin, and it's essentially shield. So it's only the top surface that the sun rays are going to get to, and it gets stopped right there. That's a practical way. In terms of really putting something on the outside, not very common from what I know, but you could essentially have a two-layer structure made by extrusion that will have the outside layer with carbon black. But what I've seen mostly is, you can have fittings that do have that, so it's only the very outside that's affected. Very good question. All right, we'll move to material specifications, and first example is this high-profile project in the city of New York that I worked on. It was a 60-foot-long fontaine wall. Very, very nice architecture. It was bronze, so all these panels, you can see how intricate the patterning were cast and, created in terms of the design one at a time. So the artist here was in charge, if you will, of the project. One of the major issues that happened there is nobody really thought what is going to happen between the summer and the winter. So if you have this big tunnel that's 60 foot long, just a little bit like when we were talking about the plastic pipe, it wants to expand and contract. So we put this here, and there's a lot of mechanical system inside that tunnel that we don't need to worry about here. But it is sitting on a foundation, so it's held by the ground at the bottom. The way it really had essentially a basement on the inside of it to host everything. So the bottom is restrained by the ground. The top really wants to expand and contract. Each panel, 8 feet long, is trying to go somewhere. And it's a big issue with buildings. And there are, I guess, different ways to try to mitigate it. In this case, the largest issue was the engineer agreed to just weld the cast panels together. So this was a 60-foot long beam of cast bronze. So what happens with cast bronze? They specified it using the Copper Development Association nomenclature. So you can go here and say, I want a C alloy. So let's say I say, please make me a C 100, 600, 10,600 number. That's what I want to use. And apparently the engineer did go to that specification and found some mechanical properties that he was happy with. Now, the real issue in a project like this, and I've seen that in other cases, is this tells you the chemistry only. This only tells you how much copper you're going to have, if you have a little bit of tin, exactly what the chemical makeup is. It doesn't tell you anything about how it's going to be cast and the type of mechanical properties you're going to get. So what happened in this case is they cast the panel without really preventing oxidation. They had a lot of residual stresses, and essentially the panels were fairly brittle. So right after the first season, and that's really funny because you ask, so when did it crack? Oh, in the late fall, just before Christmas. That makes sense, when everything was trying to shrink but couldn't. So there was a first crack that started this way, and then they said, well, maybe that one panel was wrong. So they started trying to cut this up and make a new one. And then another crack started, and another crack. And then it soon, they called for more experts, say, what's going on here? Well, what's going on is you have a lot of stresses, and you have a brittle material. Why is it happening here and it's not happening on a building? Well, the building is made out of steel. So one cycle per year, a little bit of expansion, a little bit of contraction, the welds will take it. They'll deform. You don't really see it, but they'll stretch and accommodate small variations very easily. We're not talking about a lot of cycles here. If you have 50 years, 50 times, not a problem. When we're talking about fatigue for steel, we typically are talking about thousands of cycles that become a problem for initiating cracks. That's really what we think about. So in this project, really, and it was a big design firm that had probably all the expertise in-house to know how to do better. But they didn't because the engineer in charge didn't appreciate enough the difference between saying which alloy I want versus which properties I want. So there were multiple ways. It could have been a slightly different chemistry, to tell you the truth, but there were multiple ways, even with that alloy, to cast and heat treat it in a way that it would have done just fine for this application. But when it's all assembled as a 60-foot long beam with the mechanical systems in it, it's a little bit too late to say, well, let's take each panel and heat them up a little bit so we get a ductile microstructure. That's really, really how it took. You don't have to change the casting procedure. You have, after casting, to heat it up to get a very ductile microstructure. Very sad. A lot of people were not happy. Same story with steel. So we're going to try to go through that quickly. A very common type of steel for general fabrication is an NC steel that will just be a 4-digit number. AISC. It's very, we don't even, AISI, so American Institute for Steel, I can't even remember. It's the same story where this only tells you the chemical composition. Now, for a certain chemical composition, like 1020, the microstructure could look so much different. This is a case of wrought iron where all the carbon is in these tiny lamella. This is not a way we make iron anymore, but before we could make steel, buildings were made out of wrought iron, so forging iron. And you could probably anticipate that the cracking resistance of this type of iron in this direction is going to be very low, whereas here the carbon is very well distributed. It's not brittle because each dark zone is a pearlite, so it's actually a combination of soft and hard material. So there's nothing brittle here. There's a lot of brittleness in this microstructure. But when you say 1020, you could make it either way, depending on your processing. And that's why we have a lot of material specifications that include mechanical properties. So they'll tell you what, depending on the grade, what minimum yield strength you want and the minimum elongation. You can have fracture toughness requirements. These do tend to be ASTM standards as opposed to an NC or CDA, Copper Development Association, and it's just the way it is. So most ASTM products will have not only a makeup requirement, but also a performance requirements, and specifying those is a big advantage. So if you're building a go-kart for racing and you ask for a 4130 steel that can be made weldable, so you ask for a W grade of it, it's the same story where you're just saying the chemical composition you want. You should ask for this as part of an ASTM standard for the product. So mechanical property requirement here in that ASTM. And if you're looking at high-strength bolts, so a grade 8 bolt by SAE will have composition here. It has mechanical property requirement, and it also has heat treatment requirement. They're very, very, very specific. The reason I copy this one is very rare that a standard will tell you how to temper your steel very precisely. But when it's becoming relatively high-strength material, you can't take a chance. You don't want something to be brittle if it's supposed to be a good high-strength bolt. So you go all the way to that step to figure it out. Aluminum is a little bit the same story where you have a 4-digit number originally from the Aluminum Association that tells you a little bit what's in the alloy. The reason we have so many is some of these, well, pure aluminum has application for conductivity, so power lines, for example. The 2000 series is heat treated, so it will build up strength by a special quenching and aging process. When you do 3000, 5000 series, those are work hardened. So the real way to get a better strength of that aluminum is to roll it cold to get it harder and with a greater yield strength. There's a nomenclature for cast aluminum. Aluminum silicon is very, very common with copper here. So a 300 series cast aluminum, and I think like 356, 360, and 380 probably will be at least half of what is cast for aluminum, because you can have a heat treatment. And that's a T designation. So if I go here and I say I want a T6, it tells me that it's going to be quenched and aged to a peak hardness. So that's a little bit how you think in terms of just specifying the material you want. This is a little bit in between with the aluminum, because we're including a little bit of the chemistry here with a little bit of the process. So this is really the heat treatment. Does it have a mechanical requirement? No. It's just a recipe for how to do it. So if you want to have minimum material requirement, it becomes part of an aerospace material specification. That's another kind. Or an ASTM specification that will have those minimum. Otherwise, you don't know what you're getting in terms of mechanical properties. So took a little too long perhaps on the plastics, but yeah, you guys had questions. So we'll move on to the steel pipes next week. I think it's Monday. Professor Eager is going to be here tomorrow. Thank you.